right, let's take a look at problem 2 or example 2 from chapter 5. Isobutane is heated in a heat exchanger under constant pressure of 1 bar from 220 Kelvin to 300 Kelvin. Use the SRK equation to calculate the following. A, the amount of heat, and B, the entropy generation if the heat is provided by a bath at 300 Kelvin. Additional information, we're given the ideal gas heat capacity of isobutane. All right, so it's constant and equal to 96.5 joules per mole Kelvin. And then in red here, I have a note. All right, and so my note is basically, if we use our SRK equation to state and we obtain more than one real root, we need to make a decision in terms of what route to choose. Okay, and so here I have reference data. So at my initial temperature of 220 Kelvin, the saturation pressure is 0.14 bar. All right, and so Psat, right, is less than my pressure of 1 bar. So Psat is less than P, or P is greater than Psat. So I'm going to have a liquid at 220 Kelvin. Then at 300 Kelvin, saturation pressure is 3.7 bar. So at 300 Kelvin, P is going to be less than Psat. So that means I have a vapor. Okay, so I'm actually vaporizing isobutane in this heat exchanger and going from 220 to 300 Kelvin. Now, in this course, I've been giving you reference points in order to identify what phase. Next semester, right, we would get into, GR is equal to HR minus TSR. So now that we have this mechanism to calculate HR and SR, we can calculate GR. And if I obtain more than one real root, which one I would choose, right? It's not going to be the middle one. I would look at those two end ones and compare the residual Gibbs free energy, and the one with the lower residual Gibbs free energy would be the phase that I would have, right? GR is equal to RT log phi, so it would also be the phase with the lower fugacity coefficient. And if they're both the same, well then I would have vapor-liquid coexistence, right? And you would find that middle one never has the lowest residual Gibbs free energy. All right, so let's get at the problem at hand. Right, so in A, we're asked for the amount of heat. So I start by writing my first law balance. So delta U is equal to Q plus W. Okay. So in terms of Q, okay, I'm going to write down my expression for boundary work. So Q is going to be, it's going to be Q minus the integral from my initial state to my final state, P dV. Okay, where if P is constant, this is Q minus P times the integral from 1 to 2 dV. Now what I'm going to do is, this would just be V2 minus V1. Okay. I'm just going to write this as Q minus P, and I'm going to write this as delta V. All right, V2 minus V1, I'm going to write as delta V. Okay. Why am I going to do that? Because if I take my equation and I rearrange for Q, I'm going to get Q is equal to, so if I were to bring negative P delta V over to the left, delta U plus P delta V, okay, where delta U plus P delta V, well, that's just going to be equal to delta H. Okay. Cool. All right, so remember, by definition, H is U plus PV, okay, where here my pressure is the same, all right, and so by definition, again, H by definition is U plus PV, all right, and so just for completeness, H2 minus H1 would be U2 minus U1 plus P2 V2 minus P1 V1, right, where P2 and P1 are both the same. So I'm just left with, I'm going to write this as delta U plus, okay, P is the same, so I can factor it out, V2 minus V1, right, delta V. Okay. All right, cool. Okay, so my first law of balance reduces to just Q is equal to delta H. Okay. So now in terms of calculating delta H, okay, let me box this in. So how we tackle this in the context of chapter 5 is, well, delta H, that's going to be equal to H2 minus H1. Okay. And I'm going to break that down into H2 ideal gas minus H1 ideal gas. So difference in ideal gas values plus difference in residual values, H2R minus H1R. Okay. Now for completeness, right, what I'm doing, right, is H2, right, is equal to H2 ideal gas plus H2 residual. Remember, residual property is actual relative to that of an ideal gas. right? So H2 is just equal to H2 ideal gas plus H2R. Likewise, H1 is equal to H1 ideal gas plus H1R. Okay. And what do I do this? Well, when I think about the second term, when I see this difference in residual properties, that's what I'm going to calculate using my SRK equation of state. Okay, and by SR equation of state, right, I've got some black box where if I know my temperature and pressure along with TC, PC, and omega, I could plug those into my black box and directly compute these two values and compute the difference. And then when it comes to difference in ideal gas terms, right, what I think of when I see that is I'm going to have an analytic equation. Right, I'll have analytic equations that could be used to readily compute those. Okay. So delta H, I'm going to break up into a difference in ideal gas, or a difference due to my ideal gas contribution, and then here's my residual contribution. Residual contribution, that term that results from, the fact that molecules interact and take up space. All right, so let's start with the ideal gas contribution. Okay, so in terms of the ideal gas contribution, okay, so I've got delta H ideal gas, okay, which is H2 ideal gas minus H1 ideal gas, and that's going to be equal to, so enthalpy of an ideal gas is only a function of temperature, so that'd be the integral from T1 to T2 Cp ideal gas dt. Now in the problem statement we're given a value of heat capacity which is constant, so that means we can bring Cp out of the integral, and then we're left with just Cp ideal gas T2 minus T1. So I'm going to write it down here just so I can box it up. So delta H ideal gas is going to be equal to Cp ideal gas times T2 minus T1. Okay, and I'll just leave it like that because I'll write it down when we go over to MATLAB and compute it. And then when it comes to residual, okay, again the key is going to be when I'm using my SRK equation of state is I've got some black box. Okay, inputs. Okay, I'm going to need to specify my temperature and pressure. So this could be, say, T1 and my pressure, which is just 1 bar, right, the pressure that's constant. Then I need my parameters TC, PC, and omega. That goes into the black box. Okay, and now my updated code in Chapter 5, out's going to come Z, V, then V ideal gas, just like in Chapter 2. But I'm going to add to that HR and SR, my residual enthalpy and my residual enthalpy. We'll use the enthalpy here in part A, and we'll use the entropy in part B. Okay, cool. So let's go over, and then, just for completeness, right, so my change in my residual contribution, that's going to be S2R minus S1R. Okay. All right, so now let's do it. Okay, and as I set this up, so I've got Appendix A open, but then when I shoot over to MATLAB, okay, what I'm going to start with is I have posted this M file, okay, and I'm just going to open it. We're not going to edit it. So I have posted this M file, which is my function, which is my updated SRK cubic equation of state code to now calculate my residual enthalpy and entropy. Okay. So you need to download this, right? So this you should download from Canvas. And then there's a script file, okay? And so you should also download this. They should both be in the same directory, okay? This is what I'm going to use as my starting point, and I'm going to edit and update for my problem. And so basically what I did is when I wrote my SRK equation of state code, I applied it to example 510 of the text. That way I could get an answer and compare and check to make sure it worked. Okay. And so I'm going to start with this script for 510, okay, and I'm just going to update it for our problem. Okay. And so I'm going to call this chapter 5, and I'll just do an _2 for example 2. Okay. And I'm going to start, okay, with my ideal gas contribution. Okay. And so for my ideal gas contribution, I'm going to need my initial temperature. So let me scroll up. I'm pretty sure that was 220. Initial temperatures, 220. And that's Kelvin. My final temperature, okay, in Kelvin. So I believe it's 300. right? 300. Okay. And then my ideal gas heat capacity, 96.5. Okay, I'm going to make note that that's in joules per mole Kelvin. Okay, so then I'm going to compute, and I'm going to convert to kilojoules per mole, right? Just because I expect it to be pretty big, in that this is, this is approximately 100, and my difference in temperature is going to be 80 Kelvin, right? So my DH ideal gas, okay, was CP ideal gas times T2 in Kelvin minus T1 in Kelvin, okay, where that change in temperature is 80 Kelvin, and I'm multiplying it by something that's approximately 100. Okay, so what I'm going to do is I'm going to divide by 1,000, so I get my heat capacity in kilojoules per mole. Okay, just to keep it more order 1-ish for when I then compute the rest. Okay. And I'm going to make this larger because now we need to calculate my residual enthalpy at state 1 and state 2. Okay. And so that's where this happens, right? So this is from that example 510, where I have my critical parameters that I need, or TC, PC, and omega. And then here's my temperature and pressure of interest. And then there's an example of running the code, right? And you can take a look at the example 510 video too, right, for more details, just updating that. So let me start. I have, it's here. I've got the appendix. So this is appendix A from the book. So I need to find isobutane. So TC's 407.85. So TC's 407.85. PC, it's up here. PC is 36.40. And omega is 0.186. Got it. Okay. And then I need my temperature and pressure. Okay. I'm going to delete the temperature since I have the temperature already up here. And my pressure, and the problem is 1 bar. Okay. Cool. Okay, so I have the code, and I'm just going to update it for this case. And so I'm going to update it. Well, and actually, so if I look at what I have, right, this is set up so it returns volume, residual enthalpy, residual entropy, Z, and V ideal gas. Okay. I don't care about V, so I'm just going to put a squiggly mark in there. Okay. Residual enthalpy I care about. Okay, I'm going to call this first one H1R. Entropy I care about. I'm going to need that for the second problem, for part B, so I'll call that S1R. Z I care about in terms of identifying phases, so I'll let that live. And then I don't care about V ideal gas. Okay, so I'll call those all H1R, S1R, and Z1R. And then on the right-hand side, I'm going to update this. Okay, pressure is the same in state 1 and 2, but I'm going to update this for T1K for state 1. Okay, and then I'm going to copy and paste this. And update it for state 2. So I'll call this H2R, S2R, Z2R, and that'll be T2. Okay, so I'm going to update this, and so I'll run it up to here. So I'll get DH ideal gas, and then we'll see how many roots I get for state 1 and state 2, and then based on the information, right, we should have a liquid initially and vapor finally at the final state, so that we can update our code to choose or use the appropriate route then moving forward to get the difference. Okay. So let me run this. Okay. And again, you need to have This file, even though we don't have it open and don't touch it, right, that needs to be downloaded and present in the directory because it's used here. Okay, and it looks like we do get 3 real roots. So let's start with 1. Okay, so in the first case, right, I have so there's delta H ideal gas, right, in kilojoules per mole, 7.72. Right, now my residual values are in joules per mole. Right, we'll keep note of that since my ideal gas was in kilojoules per mole. But I get 3 real roots for H, S, in both cases. Okay, so going back, okay, to the problem, right? So we said that in state 1 at 220 Kelvin, P sat is 0.14 bar. So since P is greater than P sat, then I have a liquid. So if I just do one at a time, so in state 1 I have a liquid, so that's the third root here. So third root is what I need. Okay, so what I'm going to do then is I'm going to update this. So I suppress the output, and I'm going to call this H1R is going to be equal to, okay, I just want the third root of this, H1R SRK 3. Okay, so I just want the third element from that vector. And then I'm going to get S1R. Okay, it's also the third root. Okay, and then if I look, so for state 2 here, okay, state 2, we said at 300 Kelvin, P sat's 3.7 bar. So since P is less than P sat at 300 Kelvin, well, then I have a vapor. Okay, so my vapor root, that's going to be my first one. So let me just come over here. Okay, so then H2R, okay, is going to be H2R SRK, and now I need the first element. S1 or S2R is going to be S2R SRK 1. Okay, so I've just updated it, so I'm just choosing the appropriate root. Okay, so the third element of that vector and then the first element of the vector. So now computing, and I can make this full screen again. So now computing the residual difference, and I'm going to do this in kilojoules per mole. Okay. Remember from the comments here, H2 or HR is in joules per mole, and so I calculate the ideal gas difference in excuse me, kilojoules per mole. So we'll keep this the same. So DHR, right, so I use similar notation. DH ideal gas, so DHR is going to be equal to H2R minus H1R. Okay, and I'm not going to suppress this so I can see the two differences. Oh, and I get to divide by 1,000. Okay, and then so computing, I'm just going to call it DH in kilojoules per mole. Remember, DH is just Q. Okay, so DH is just going to be DH ideal gas plus DH residual. Okay, so let's see. So if I run this, I've got to minimize it. So if I run it, I get DH ideal gas, which is 7.72 kilojoules per mole. DHR is 23.2314 kilojoules per mole, and then there's delta H. So we see that, the residual contribution is fairly large. Okay, and remember, this is the contribution that's going to count for my phase change. Okay, so this is just the difference in an ideal gas at 220 Kelvin and 300 Kelvin. Okay, this is going to be the contribution that actually corresponds or accounts for vaporization. And so we don't need an explicit enthalpy of vaporization term, right? It's captured by our cubic equation of state. Okay, so I just want to come up here and write these values down so that we have it, right? It makes sense. Delta H, we expect it to be positive. I call this, S here. This is going to be H, but we'll get that. Delta H is going to be positive because I'm vaporizing it, right? So this is 7.72 kilojoules per mole, right? And we'd expect this to be positive since I'm heating up my ideal gas, right? This is my ideal gas contribution. Since I'm heating up an ideal gas, that's going to require energy. So that's positive as we would expect. Okay, and to make this delta H. So delta H residual, right, was H2R minus H1R. And that was equal to 23.2314. 23.2314. Okay, and that's also positive, right, for our vaporization. Right, and logically, rationally, it should make sense. As I go from liquid to vapor, right, that's going to require heat, and so I get a positive residual contribution. And so then my total, right, delta H. Oh, and actually I have that up above. Right, delta H. I thought I did. Q's delta H. Yeah, it's delta H ideal gas plus delta H residual. I guess I didn't have a spot for it, so let me write it here. So Q is equal to delta H, and that's delta H ideal gas plus delta H residual, and that's equal to 30.9514. 30.9514 kilojoules per mole. Sweet. Cool. Okay, so that's the first part. So we calculated Q. Now in the second part, we're asked to calculate the entropy generation if the heat's provided by a bath at 300 Kelvin. So calculate the entropy generation if the heat's provided by a bath at 300 Kelvin. All right, so what are we going to do here? Well, what we're going to do here is my entropy generation. It's going to be equal to the change in entropy, so delta S of my system. Okay, let me write the system first, plus delta S of my surroundings. Okay, where if I assume that my heat exchange or heat interactions with the bath, then delta S of surrounding is just going to be equal to or equivalent to, I'm going to write as delta S of a bath. Okay. All right, so now I'm going to take this term first, right? So what am I going to do? Well, delta S of a bath, okay, is just going to be equal to Q bath over T bath. Okay, so T bath is the temperature of my bath. Okay, in terms of Q bath, well, how I handle this is any heat that is any heat that is heat being added to my system, well, it must come from my surroundings, right? So any heat leaving our surroundings enters our system, just like any heat that would leave our system, right, would go to the surroundings. And so, what that does for us is, well, Q bath, right? So Q bath or, Q surroundings, right, is just going to be equal in magnitude to the heat of our system, Q system, but an opposite sign. Right, so it's going to be negative Q system over T bath. Whereby Q system, I'm going to erase the superscript SYS because that's just Q as we just calculated in the last problem. Okay, and so the key is the heat leaving the bath and being delivered to our, so heat leaving our bath, right, is being gained, is being added to our system, right? Just like if we had heat being removed from our system, that'd be heat that'd be delivered to our bath. So the heat, right, it's going to have the same magnitude. So Q bath is the same magnitude as the heat we just calculated, the heat that's added to our system, but it's going to have an opposite sign. Okay, so delta S bath I can calculate because we just calculated Q, and then T bath would just be our 300 Kelvin, right? So T bath, that's 300 Kelvin, and then Q, right, that's going to be equal to delta H, which we just calculated above. Okay, so we'll head over to MATLAB and we'll calculate that in a second. Okay, but then we also need delta S of our system. Okay, so delta S of my system, well, that's going to be entropy of my final state minus the entropy of my initial state. Okay, now in the context of chapter 5, okay, we break this up. I'm going to break this up as S2 ideal gas minus S1 ideal gas. So ideal gas contribution plus residual contribution S2R minus S1R. Okay. And again, the idea is when I see this difference in residual contributions, that's what I can compute, or I'm thinking about using my cubic equation of state. We'll calculate that using our cubic equation. And when it comes to an ideal gas, right, I'm thinking analytic expressions, right? I'm going to have analytic expressions that can compute that. Okay. All right. So let's start with the ideal gas contribution, right? So how am I going to calculate the ideal gas contribution? Well, from part one, we said that my first law of balance for this case reduces to Q is equal to delta H. Okay. All right. Well, Q is equal to delta H. Now, if we assume that the heat exchange is reversible, well then Q is going to be equal to what? T times delta S, right? And now what I need to do is when I write this, though, I need to write it in its differential form, right? So in its differential form, I'd have that del Q is equal to dH. Okay. Now for a reversible process, right, del Q is going to be equal to T ds. Okay. So for the reversible case, right, so if I have reversible heat exchange, then del Q is equal to TdS. And we just showed from part A for our first law of balance that del Q for this process, this constant pressure process, is equal to dH. Okay. Well, what do I do with this? Well, this tells me then that, so dH, all right, is going to be equal to TdS, or solving for ds then, ds is equal to 1 over T dH. Okay. Where dH is equal to, right, dH is equal to Cp dt. Okay, so this is going to be equal to Cp over T dt. Okay, now we're considering the case of an ideal gas. I'm going to put a superscript Ig, superscript Ig, superscript Ig. Okay, so ds ideal gas is equal to Cp ideal gas over T dt. Okay, cool. So if I need to calculate S2 ideal gas minus S1 ideal gas, that's equal to the integral from my initial state to my final state, ds ideal gas, okay, which is equal to integral from my initial state to my final state, Cp ideal gas over T dt, where again my heat capacity is constant, so I can take that out. And I have Cp ideal gas times the integral from my initial state to my final state, 1 over T dt. Okay, so that S2 ideal gas minus S1 ideal gas is equal to Cp ideal gas. Okay, so integral of 1 over T dt. So this is going to be equal to log T2 over T1. And yeah, that's it. So delta S ideal gas, so S2 ideal gas minus S1 ideal gas is just Cp ideal gas times log T2 over T1. And so I've got this ratio of temperatures, so I need to make sure I'm using absolute temperatures here. And then again, when it comes to my residual contribution, right, I'm thinking about SRK equation of state. And so I've got this black box. Okay, ring goes. I need to know the temperature and pressure along with TC, PC, and omega. And then out comes the context of chapter 2, V, Z. Okay, then I had to compute V ideal gas as well. And now it's also going to give HR and SR. Okay. And we already got the code working in part A to get us the residual entropies. Right, so we're already in good shape. Okay, so let me just put some placeholders in here. So we'll go over them. We'll calculate S2R minus S1R. Okay. And then delta S. Okay, essentially is delta S ideal gas plus delta S residual. Okay. And so we'll compute delta S systems, and then we'll also calculate delta S bath as we jump over as well. Okay, so let's get it. Okay, so jumping over to MATLAB here. I'm going to make this full screen. Okay, so we already isolated the entropy. Okay, entropy now, note is in units of joules per mole Kelvin. Okay, and usually units of joules per mole Kelvin for most of our problems works out. So I'm going to calculate DSR since we have it. Oh, computing entropy in, and I'm just going to make a note. I'll just keep everything in joules per mole Kelvin. So my residual contribution DSR, that's just S2R minus S1R. Okay. Where up here, right, we already made sure we selected the appropriate root. Okay. DS ideal gas. Okay, we had this variable CP ideal gas, right? CPIG times log T2 over T1. Okay, making sure I gave them the right names. Yep. And so then ds is equal to ds ideal gas plus ds residual. Okay, so I've got that. So now computing entropy, and I'll write of system. Okay, now entropy of bath, and again we're in joules per mole Kelvin. Okay, so T bath was 300 Kelvin. Okay, and so ds bath, okay, is going to be equal to, well, negative Q, right? Q is equal to dH, so it's going to be negative dH. Now dH here is in kilojoules per mole. Okay, so I'm going to multiply that by 1,000 to get it in terms of joules per mole. All right, so it's Q, which is equal to delta H. Okay, and I multiply by 1,000, so it's joules per mole, and then I divide by T bath. Okay, so it's this divided by T bath. Okay, cool. So there's ds bath. Okay, and I don't need parentheses here, right? It's just multiplication. And so then Sgen, okay, in joules per mole Kelvin. Well, entropy generation we said was equal to, so I'm going to call this Sgen, was equal to ds, which is delta S of my system, plus delta S of my surroundings, which is ds bath. So if I run this, okay, so now I have, there's my residual change in entropy for my system, the ideal gas contribution, and then the total change in entropy. Okay, and that makes sense, right? So delta S of vaporizations could be positive, right? It's going to be delta H of vaporization divided by T, right? And that'd be vaporization at the same temperature. But key is delta S of vaporization is positive. Okay, so let's write these values down here. So residual contribution 89.4233, 89.4233, and that's joules per mole Kelvin. Okay. My ideal gas contribution 29.930, 29.93, 29.93, 9300, and that's joules per mole Kelvin. And then delta S of my system, that's 119.3533 joules per mole Kelvin. Great. And then my entropy generation, my entropy of my bath, which we had up here, but let me write it down here so that I have space to do so. Delta S bath is negative 103. Negative 103.1714. That's joules per mole Kelvin. Okay, and so then finally Sgen, my entropy generation, is 16.1819. Okay, and that's joules per mole Kelvin. Okay, and my entropy generation is positive, right? Cool. Okay, so Sgen's greater than 0, right? All checks out. So hopefully that helps, right? I think the key is when we're calculating these change in our properties, right, in chapter 5. Let's see, is if I'm trying to calculate the, delta S, so the change in some property, here we had H and S. I'm going to write it as a difference in ideal gas contribution and a difference in residual properties. Key is the residual contribution. That's what we calculate using our equation of state. And when I think about my equation of state, I think of my black box. In goes temperature and pressure, along with my parameters Tc, Pc, and omega. Out's going to pop HR or SR. Okay, so I can calculate, right, essentially the absolute value of these quantities. And then when I think about the ideal gas term, right, I think about, I like, ideal gases. One of the reasons is we have analytic equations. So this difference we can calculate analytically. Okay, hope that helps. I'll get this posted along with my MATLAB code. If you have any questions, let me know.